יש קשר ריכוז. זה בסדר.
אף אחד לא מתחבר בזום, נכון? מהמיץ, נכון?
מה אני יודע? Questions so far.
איך מתחבר לזה שדיברת על אוסילטור הרמוני או שכבר לא? כאילו
The question was regarding harmonic oscillator. How is it connect? How does it connect? So let's draw the harmonic oscillator as a reference, and we're gonna get back to how it connects in 2 minutes when the nice lady, our superhero, will leave. כולם רואים את הסיסמה. מה קורה?
אתם מוזמנים לעשות את זה בפעם הבאה, תרשמו.
יכולים הודעה, אני אעשה את זה. לא. תעשי סטארט ריקורדינג, לא? או שזה כבר מקליט ליוטיוב גם ככה?
כן, אבל מפה יהיה סאונד גם ככה. בהצלחה.
תודה. Great. Welcome, new guys. Next time, just come here. Perfect. So, when we have some particle, some probability of some wave that comes from -infinity with some positive energy, then we have oscillations. So when I draw the lines, what I want to do is like an oscillating wave to the right. I know that unless E, the energy is infinitely large, and if it's infinitely large, we don't care about this small trap. We know we're going to have some, let's say this is A, E to, we're going to have some B, E to the minus I, K, X, some reflected wave. Then we're going to have, and this is going to be very similar to what we did last time. We're going to have some C, E to the I, K, X, and D, E to the I, and then here it's going to be Q, because the medium is here we have different potentials, so we're going to have different wavelength. And here we're going to have minus, and here we're going to have ABCD. Let's call it F E to the I K X. It's the same wave vector because it's the same potential. This is all good and well, but now I have a different question. The question is, maybe if we have an energy which, maybe we don't have anything that stays in here in the middle. Meaning, do we have energy levels here? So it's very easy to think about the fact that if for the harmonic oscillator we have infinite amount of discrete quantized energy levels, we're also going to have something similar. But let's say this is the energy levels, and I can have here a few more lines. So E2, E3, E4. But also, maybe V0 is very small. Maybe it's so small that instead of looking at something like this is for V0, we can have some V0 tilde, which is which is much smaller than our original V0. We can have a really small bump or a really small trap. Will we have any energy levels? What will they be? Great question. Today we're going to talk about it. Okay, questions so far? So, for our example with C e to the I k x and D e to the minus I k x, this is all kind of known for us. We know how to play with it from last lesson. Today I'm gonna have something easier to solve, something which is a little bit more simple for our example, and then we will actually try to solve for those energy levels. Okay, so we're gonna do something which is called half finite potential. infinite for negative x. 0. X smaller than x. Not for x larger than that. So first of all, because the potential is infinitely large for negative values of x, I can immediately say the wave function, the probability to find some particle in this area is 0. So let's say we have some let's say we have a particle with mass m. This is the Q particle, and he is in some energy level. When I mean some energy level, I mean like bound, like trapped at some place. So our question is what those energy levels can be. So this is question number 1 is gonna be what are the possible energy levels. This is question number 1. Question number 2 is what is the minimal V naught? So the second question means what is the minimal V naught such that we have at least one energy band, at least one possible energy level for the particle to stay trapped. Okay. How would you attempt to solve this question? Ideas. What do we do when we have a potential and questions? What's the first thing we do when we have an exam? We are now in the exam. This is the big moment of your life. We first write the Schrödinger equation. H psi equals d psi. We can always write it, it's always true. When the potential is time independent, it's even easier, because we can just skip ahead and say everything depends on x, and we don't care about the time dependent for the time being. So it's minus h bar squared over 2n dou x plus v of x psi equals e psi. Okay. What is the second step we do? Perfect. She said split according to different potential behaviors. Different potential behaviors, it's the same as saying different Hamiltonian acting in some sense. Not exactly, because it's the same Hamiltonian but different potential regimes. So we can say psi of x is equal to, and for x, for negative values of x, we're going to get 0. For x between L and 0, we're going to get, let's call it psi 1 for now. And for x larger than L, we're going to get psi 2. I want you to try and think one step ahead of me, if you can. Not say it's easier. I don't say it's easier. Just say this is some familiar regime. So what is psi 1? I can just put it inside the Schrodinger equation and solve it. So for this regime of x, we don't have any potential. So I can just write 1 minus h bar squared over 2m psi 1 second derivative is equal to e psi 1. Psi 1 second derivative is equal to 2m e with the minus over h bar squared psi 1. Psi 1 is some a e to the I kx plus b e to the minus I kx, where k is square root of 2m e over h bar. Now for psi 2, the same procedure. Another thing which is important, as we can recall from last time, is what is larger, V0 or E? Why is it so important? So what we can do, we can say that if the energy is larger than V0 or the other way around, we're going to get different behaviors. But first of all, I think I did an oopsie, yes. It's supposed to be E minus V dot, right?
Yeah.
Don't do that?
Yeah, that's correct. That way.
Yes, because of the minus of course. So here we can take, so E, because we assume that if we want to assume that the energy level is smaller than V0, because we want to look for some bound states, bound states, meaning states which are trapped here. So this quantity, we can call it q squared and say this must be positive. This is for E smaller than V0. And I can just write straight over here that we're going to get some C e to the qx plus d e to the minus qx. Was it too fast? A little bit? Okay, so I just solve this. But this is interesting because if q squared was smaller than e, meaning if we had a large amount of energy, which is larger than the potential, we would get that q is some imaginary number, some pure imaginary number. And then instead of some exponential growth or exponential decay, we would get oscillatory behavior. We can also observe something very interesting. We can observe immediately, and this is immediately when I'm about to stop. So, if we look at psi of x, when x goes to infinity, because here we have something which is real and positive, here we have something which is real and negative, when x goes to infinity, we have that e to the qx goes to infinity. הצלחתי.
כן הצלחת?
לא.
לא.
When x goes to infinity, this explodes. It doesn't make any sense. Because if we allow this part to exist, we will never be able to maintain the normalization of psi. Meaning I can erase this and say that because psi of x goes to infinity must go to 0 for the wave function to be normalized, I can immediately erase this part. And of course, this is all I can just put it in. I can put it in red. That we assume that E is smaller than V naught. It's very important. Otherwise, we can have oscillations that go to infinity, but we don't because we're gonna have some bound state. What we have here? Let's examine the model.
סליחה, מה אמרת לי קטן ב-0? על כל המקרה הזה?
Yes.
סבבה.
Our system is about E smaller than V naught because if E is larger than V naught, we wouldn't have Q squared larger than 0, not necessarily, and then we might have oscillations. Okay. So I can write Q is equal to.
אבל גם עכשיו יש לנו oscillations, כן?
Yes, but we have oscillations only in this regime. So we're gonna have here some oscillations, maybe some energy bands, and then we're gonna have here exponential decay,
אוקיי. תודה.
which is gonna be d e to the minus qx. Yes.
You wrote there for E smaller than V naught, Q
Yes.
squared is bigger than 0,
Yes.
but
We define this. I'm gonna write it
only
here.
we get a complex number there.
Sorry, again.
We get like a negative number, no?
If e is smaller than v naught, we get here a negative number. Here we have some minus, I don't know, let's call it a yam, minus yam. And minus, and where yam is a positive number because e minus v naught is negative, so minus v minus e. Okay, I can just write it as. Let's write it down.
Okay.
I can write it as v naught minus e
Yeah, okay.
2m over hy. And if e is smaller than v naught, this is positive, positive,
Yeah,
positive.
okay. Sorry,
All
I
good.
didn't notice this.
Never say sorry for a question. Never. It's good to ask questions. So, this is our system. Okay, so the first thing when we interact with a question, examination, like final exam level question, this is what we have here. The first thing is to draw. The second thing is to think. Then we write the Schrödinger equation because it's always useful. What is the next thing? What do we want to find? What do we want to do?
E גדול ב-0.
No, let's assume E is smaller than V naught throughout everything.
What did we want to find?
We want to find the energy levels, what are the possible energy levels for x between L to 0. By the way, what are the possible energy levels for x larger than L? They are none, because here we have exponential decay. The particle can't stay here forever in a sense. Like we're gonna have some probability over here, but it's not that the particle is bound to some energy level here. The probability of him staying here is exponentially decaying. When is it important, this exponential decay? First of all, it's always important, but it's especially important when we have some finite barrier, where this is V naught and our energy is E smaller than V naught. The exponential decay is going to be such that some particle or some probability will be able to transmit the barrier. So if it's finite in its length and in its height, we can go through the barrier, and then maybe here it might be bound to some energy level. But here, because it's infinitely long, it's only decaying. And it doesn't have anywhere to tunnel through. So, how do we find the energy levels? What do you mean by energy levels? When I say energy levels, I mean K and Q. What is the next step? Perfecto. Amazing. Boundary conditions, why? Because when we impose boundary conditions, we basically, right now we have 1, 2, 3, let's call it 3, because K and Q are the same, it's like E. If I know E and know K and Q. So I have E, which is 1, A, B, and D. So I have 4 unknowns. The only way to get rid of them and to find them is to use some conditions or some restrictions over the system. One restriction was that psi of x must be normal. Another restriction is that psi of x equals 0 is equal to zero. Perfect, because here we can't find a particle and the wave function must be continuous. It's good to think. Let your brain work, huh?
Okay.
It makes sense?
Okay.
Because if it's something finite, let's say it has some probability to be here, so it must have some probability to be at 0 minus, because the wave function must be continuous at every point.
Okay.
Also, the wave function must be continuous at every point. So we can impose that psi of x equals L minus must be equal to psi of x equals L plus. Because we don't have here a delta function or something which diverges or not well behaving, we can also say that the derivative of x equals L minus is equals to the derivative of x equals L plus. So we can write it as 1, 2, and 3.
why the derivative?
Why the derivative?
כאילו למה לפי מה התנאי הזה? שהנגזרת צריכה להיות שם גם בצד?
רציפות גם כן.
So we're going to answer first in Hebrew and then repeat it in English. אז אנחנו יודעים, השאלה היא, אוקיי, אני אעשה את זה ואני אגיד, תעצרי אותי. Okay, I'm going to do it in English. The question was, why do we know that the derivative is continuous? Because the wave function is always continuous, but the derivative is not necessarily continuous. It is necessarily continuous when you have some well-behaving potential. For example, what is not well-behaving potential? And it is something which behaves like a delta function. And we can have an example. So, when we look at the Schrödinger equation, we have minus h bar squared over 2m psi second derivative of x is equal to e minus v of x psi of x. Let's say I want to have a continuity condition at some point x naught. X naught could be 0, it could be m, it could be whatever. I can always integrate both sides. Instead, let's say minus h squared over 2m, x naught minus epsilon, x naught plus epsilon, psi, and I can write it as d squared of psi over dx squared dx is equal to an integral from x naught minus epsilon, x naught plus epsilon, e minus v of x psi of x dx. Now, here, because this is an integral of a derivative, it's really easy to say we just have squared over 2m. We can have psi, derivative of psi, at x naught plus epsilon minus the derivative of psi at x naught minus epsilon. But on the other side, let's consider. So here, what we have from x naught minus epsilon to x naught plus epsilon, e psi of x dx plus integral v of x psi of x dx from x0 minus epsilon to x naught plus epsilon. Let's consider this. First, this term of the energy term. As long as you have finite energy, okay, even if you don't have finite energy, we can just take the energy over here. We can always assume the energy is finite. And then what we have some integral on a very, very small region of something which represents probability. This cannot diverge, so it must go to 0. So this term always goes to 0. The potential, on the other hand, might vary. It might be very interesting. Moreover, it might go to infinity. For example, if v of x is equal to delta of x, and we can hand in here some constant, beta, then we're going to get psi, then let's write it. It's not enough to have here delta of x. It must be delta of x minus x naught in our case. Then we're going to get psi of x naught. But otherwise, for any finite potential, even if the potential is not an analytical function, but it's finite, meaning when we integrate over this very small regime. So we have some very small number multiplied by another very small number, psi of x. We get 0. הבנתי?
Yes, תודה רבה.
אוקיי.
אם גם אני שואלת שאלה ארוכה מדי, אתה יכול להגיד לי כאילו אחר כך.
אוקיי. אמרת לו? But it's important to ask questions.
מה החלק האחרון? עוד פעם. This part, yeah.
This part, yeah, it's important. It's not some.
Yeah, I get the first part, but
Here, what we have a potential. So if the potential is finite,
okay.
then let's say it's some v naught, and you multiply it by some probability density. It's not a probability because probability is multiplied by this delta x, but this delta x goes too small, very, very, very fast. So we have here something very small multiplied by something else, which is very small. So we get 0, basically.
Okay.
When we don't get 0, when you have a potential which diverges exactly at the vicinity of this x naught. What they would have been by divergent potential, I mean like delta potential.
Yeah, seems like then by definition you get
By definition.
the definition of delta.
And we really love to have those examples. We're also
Yeah.
going to have some example of these sorts today.
Okay.
Can I rest this part?
Yeah.
כן, תודה.
Okay. Great. Okay. So, condition 1. Condition 1 tells us that a plus b equals 0. So we can write b as minus a. So I'm gonna write this wave function a little bit better. A to the I k x minus a to the minus I k x equals to and I can write it as a tilde, because we have a factor of 2, sine of kx. Does it make sense? Yes. Why not? We know that for x equals 0, we get 0. For x equals L, we don't know. We haven't figured it out. If it was an infinite potential, well, meaning here it was also the potential was infinitely strong, or V naught goes to infinite, we would get some quantization on this k from the boundary condition on x equals L. We're still gonna get quantization condition on k using this boundary condition, but it's gonna be a bit different because this is some finite potential. I'm just gonna write a sine of kx. Perfect. Two. Okay. 2 and 3, I don't want to bore you with the details, but basically we have something quite easy to solve. And what we get is that from 2 plus 3, we get that a sine of kl is equal to dE to the minus ql, and ka cosine of kl is equal to minus q d dE to the minus ql. So we can basically just take those two equations for the first one and just put instead of x l, and we get the first relation. For the second relation, we just take the derivative first and then imply x equals l. Okay. Very interesting. So first of all, I can immediately say from here, using the first equation, I can write d is equals to a sine of k l times e to the ql. Right? I wrote it in this form, so it will be clear, because x is always larger than L, so here we always have some negative exponential. So we still have a negative exponential decay. However, it's not exactly exponential like this, it's more like this. It looks more like something like this, because of the sign. Questions? Okay, now we have almost anything, because we basically only have q and k, which are the same variable in terms of what we don't have solved. We are yet to solve, and you have these two equations. So from these two equations, I can get two unknown variables. The first one is d. The second one would be somehow k, q, e, and this is the hard part. So I'm gonna do a trick which looks like some black magic, but it's very important to do. I'm gonna divide the second equation from the first equation. Okay, so I'm gonna get ka cosine of kl divided by a sine of kl equals to 1 over q, minus 1 over q. wherever I want to put it. Okay, let's do it like this. So I get cotangents of KL equals to minus Q over K. So I said the second divided by the first, and I did the opposite on the right side. Okay. Are we happy? Think the dogma? That's all I know. Don't get. I know like 2 or 3 phrases. Okay, perfect. So what do we have here? We have some, like we can find the relation between K and Q somehow, right? But it's not very clear because let's say you had some K squared L squared equals to Q over K. It was very easy. We could just say Q equals L squared times K squared, right? This is very easy, but here we have something which is more difficult to analyze. Yes. This is what we need to analyze, right? We don't have here not A and no D. We only have K and Q. And we can find some relation between them that will give us the quantization of the energy levels over here. If it was a simple equation, for example, K squared L squared equals some Q over K, we would be able to solve it very nicely. Or maybe if it was some sine of KQ plus L equals 0. I'm inventing some relations. I would say, okay, so KQ plus L is equals to n pi. And then we get the quantization. But here we have something a bit weird, a bit different. And this is going to be the core of this lecture. Understand? So I'm going to erase the right part, rewrite this relation, and start analyze. So first, I'm going to write cotangents of K equals to minus Q over K. So this is what's called a transcendental equation. I don't know. It's not transcendental.
Yeah. Transcendental, nirali.
Exactly. Whatever.
Yeah.
Anyways, it's something that what it means is we have some equation on the left, some equation on the right, and we want to see where it connects. I'm gonna explain it more carefully in a bit. First, we can write it in terms, instead of K and Q, in terms of E and V naught. And we are gonna get, after a little bit of algebra, we're gonna get cotangents of 2ME square root over HL equals to minus square root of V naught over A minus 1. Okay, we're gonna do just another last black magic trick where we're gonna use some dimensionless quantities. We're gonna define theta, square root of 2ME over H bar L, and theta naught, square root of 2MV naught over H bar L. This is only to make it look easier. So we get that cotangents of theta is equal to minus square root of theta naught over theta squared minus 1. Just you can convince yourself it works. Don't want to get into it. So okay. Please stay focused. This is the hard and interesting part. How is cotangents of x, and I can write it x or I can write it theta, and this is a function of theta. How does it look like? So you can use decimals, or you can believe me, it looks something like this is pi. My drawing skills are not great. I'm doing my best. This is right. So the dashed blue line is going to be cotangents of theta. I'm also going to ask what the right side looks like. But first, so the right side, it's clear that it clears that we have some sort of square root of some function. We also know that in order to have real solution, we must impose that theta naught is smaller than theta, right? Okay, let's do it carefully. Theta naught over theta is smaller than 1, because if it's is larger than 1, because if it's smaller than 1, we're going to have something imaginary. Right? Correct me if I'm wrong. Perfect. So, theta must be smaller than theta naught. Very, very nice. Very, very nice. So when do we have? So if I'm gonna draw the right hand side, okay, I'm gonna get for theta goes to 0. I'm gonna have here something minus infinity. So we're always gonna get something which diverging to minus infinity at the start.
שאלה.
כן.
למה אנחנו לא יכולים שזה יהיה פה?
So the question is why we can't have here an imaginary answer. If we have an imaginary answer on the right hand side, we don't have something on the left side, because the left side is a cotangent function. It's always real.
Okay.
So if the left side is real, the right side must also be real. Perfect. I'm gonna draw a little bit more and then we can talk about it. So this is the hard part, because you need to really think about what happens here. So let's have here, let's say this is 3, this is 6, and this is 9. Let's draw in the red line the trajectory of the right hand side for theta naught equals 6. It will look something like this. Why? Because theta must be smaller than theta naught, so it ends at 6. And when theta is equal to theta naught, we have here 0 on the right hand side. For this example, we have two places or two solutions to this equation. We're going to have like theta 1, let's say it's theta 1 star. Let's call it theta 0, 1. So theta 1 star is going to be, let's say 2.9. I don't know if it's exactly the right answer. Just to get here a number, for example, the theta 2 star is going to be equal to around, let's say, 5.8. Star indicates the places where we have a solution for this equation. Meaning for this, theta naught equals for theta naught 1 equals to 6. Let's do it like this. For this case, so theta naught equals 6, we're going to have some connection over here, and another one over here. Okay, let's talk about it a bit more length because it's a little bit hard to grasp. So what we did here, we tried to find some condition on Q, K, or basically on E, on the energy. And what we got some equation, transcendental equation, which in order to solve we're going to have a solution of the sort of some series of theta I. Theta i's are the corresponding places, corresponding theta values, where the left hand side is equal to the right hand side. I'm gonna repeat it in Hebrew, but ask me if you don't understand it, if you didn't understand the English. אז, יש לנו משוואה טרנסצנדנטית, יש לנו סט של פתרונות. אני מסמן אותה בתור תטא I. והם הכל הקורות שבהם יש חיתוך בין הצד השמאלי, left hand side, הצד הימני, right hand side. Questions? Okay. So we have a series of solutions. For each theta, which is a solution, let's say I know 2.9 is a solution. I know that the energy, the correspondence energy from this equation gives me the... So from this equation I get from theta I, the energy I. So when we have a series of theta I, it means we have a series of EI, the energy levels possible. Let's draw another example. Let's draw an example for theta, this is going to be in black, theta naught equals 9. So we know we're going to finish here. We're going to diverge here, and we're going to have something which looks like this. So we're going to have here one solution, two solutions, three solutions. Or for theta naught, if I draw the example of, let's do it in the theta naught equals 9, we're going to have 1, 2, 3 energy levels. For theta naught equals 6, we are going to have 1, 2 solutions.
קצת התבלבלתי, לפי מה אנחנו בחלק בין x0 ל-L?
Okay, so the question was, how do we know we are considering this part? So we know we consider this area, and we see that we didn't get it by considering all of this here. What we did, we considered this point, x equals L. From this point, from this boundary condition, we got the quantization of energy levels. So what we did, we took psi of x and we imposed two conditions. The first was that psi of x equals L plus equals psi of x equals L minus. The second one was that psi derivative of x equals L plus is equal to psi derivative at x equals L minus. We took those two conditions, we divided between them, and we got exactly this equation. Then we implied a little bit of change of variables to make it look easier, just to have some dimensionless, unitless variables, and we try to solve for it. So we impose, okay, let's assume we have some specific theta naught. And when I say some specific theta naught, it means some specific V naught, because L is known, M is known, H bar is known. So for each theta naught I'm going to tell, let's say 9, I can find you what is the potential, the relevant potential. what I'm saying here is I don't know how to solve it exactly. I can't just give you some analytical expression and say, okay, the energy levels are. I need to numerically or graphically or schematically work very hard and give you for each specific value of the potential V naught the energy levels which are possible.
האמת, טוב, התכוונתי שאיך אנחנו יודעים שאנחנו בחלק בין x שווה 0 ל-L ולא מ-L והלאה, אבל L והלאה לא מקוונטט, נכון?
No, not exactly. Almost. The question was, okay, so we are quantizing this area, but here it's not quantized. But it's not exactly, because what we are doing, we are finding a condition on EIs, possible energies. Okay? So when we have a specific EI, let's say the energy levels are EI equals 1, 2. Okay? Can I erase the questions? Because we are in a good, better place. Let's do it. So EI, the possible options are E1 and E2, which equal, and let's say it's just 1 and 2. So Ki are going to be equal to square root of 2m over h bar and square root of 4m over h bar. This is clear. Just put it here. Qi is going to be equal to minus 1 minus v naught 2m over h bar squared. And here it's, I think it's, I'm sorry. No one fix my mistake so far. That's the square root here. And minus square root of 2 minus v naught 2m over h bar. Okay? So when I have the energy levels, and in order to get the energy, possible energy levels, I must have the potential to know what is the potential, because the energy levels, the amount of energy levels depend on what is the theta naught or what is V naught. I can tell you what are the allowed Ki's and the Qi's. What we said here, we said that there is no bound states. It's different from there are no energy, quantized energy levels. So for what I mean is that let's assume we have two energy levels. A graphical, not two, way to think about it is that for this energy level, let's say this is E2 equals 2 and this is E1 equals 1. Here we're going to have some oscillations until it goes to 0. So this is the bound state and this is the exponential decay. For the other one, let's draw it in blue. We're going to have some other oscillations, maybe smaller oscillations because the energy is a bit smaller. But the oscillations, the blue oscillations, are related to this energy, and the red oscillations relate to this energy level. Perfect. So, we have a transcendental, I need to see how to say it for future lessons. Transcendental equation. We solve it schematically or numerically. We get the possible energy levels. Or the possible theta I. It's the same. They are equivalent. They are 1-to-1 ratio. Okay? Our second question was, what is the minimal potential variable, the smallest V naught, which still allows us to have at least one bound state? How would you tackle this question? When I say the minimal V naught, I mean the minimal theta naught.
Yeah.
Okay. What is it?
So maybe the first חיתוך הראשון.
Exactly. So if I'm being more precise with the drawing, for cotangents, I draw it terribly, and I'm sorry for it. For cotangent, yes, when we have here pi, here it's pi over 2, we're gonna have something which looks like this. The cotangent theta meets the axis exactly at theta equals pi over 2. So the minimal theta not minimal, is going to be exactly pi over 2. And it's going to look like this, where here we have a semi-bound set. So if we have something which is smaller, we're not going to have any values of theta, which this equation holds true for. So our condition was theta naught is larger than pi over 2 to have, or larger or greater or equal to, meaning square root of 2 m v naught over h bar larger or equal to pi over 2. So we could just write, let's write h bar pi over 2l squared. V naught is greater or larger than this 1 over 2l. Right? Where did I write it? I'm not sure. So I wrote it a bit ugly, but it's true. This is the condition on the V naught, such that we have at least one bound state. Okay, and now we can solve it all the way, meaning we can have a final solution for everything, because we know what are the EIs, we know the Qs, we know the Ks, we know everything, we don't know A. How do we find A? Another condition, exactly.
Yes.
What is a condition we haven't used yet? I'm not gonna continue this lecture until someone gives me the correct answer.
We used all three boundary conditions.
Sorry?
We used already all the three boundary conditions.
Correct.
להתחלה אולי או משהו כזה.
So one way to look at it is initial conditions. Correct. We don't have to use initial conditions to solve it. It's true we can. It's true we definitely can use initial conditions. This is one way, but another way.
אמרנו שזה דועך, כאילו הפונקציית גל.
This is one boundary
אולי
condition.
שם יש רחוק.
Okay. The three boundary conditions we used are the boundary conditions we used are at x equals 0, x equals L, and x goes to infinity.
השתמשנו בזה?
We used all the boundary conditions. What else do we have left to use to find A?
Normalize.
It's fish and how? It's good? It's in the back?
Yeah,
Fish and how?
yeah.
Yeah, great. Very good. The normalization. We can always say that there is the probability to find the particle from minus infinity to infinity must be equal to 1. We haven't used this condition, the normalization condition. If we use it, we find A. You can see it in the lecture notes, how to do it. Right, let's look at it with some stupid attitude. Okay, questions on this, regarding this example. All is great, you understand? You understood it? Perfect.
בעצם מראש כבר מההתחלה בעצם כשאני חושב על זה?
לא, זה שונה. תנאי התחלה, okay, so the question was, aren't the normalization condition is initial condition? So not exactly, because what we imposed here, what we're gonna have in the end, we're gonna have psi of EI, such that for each specific possible energy, we're gonna get some normalized wave function.
Yeah, no.
What we want to do,
Okay.
what is the total psi? We're gonna have a sum over all EI, all possible energies. We're gonna have CEI, psi EI.
Yeah.
And these coefficients of the distribution of where are we starting between the energy bands is gonna be determined by the initial conditions.
Yeah, okay.
Good?
C זה אמפליטודה?
Hmm?
C קשורה לאמפליטודה?
Exactly. C is the probability amplitude.
אוקיי.
It's like the probability to be in the specific energy EI. We are low on time. Okay, right? We have 20 minutes. Like it was good how we went through in depth. So I'm not sorry for how I did it, but we don't have a lot of time. Okay. So I'm gonna start the second example of this tutorial, and what I'm not gonna finish, you can just read it. But I'm not gonna rush through it because I think the steps are important. So, the potential we're gonna examine now is an infinite square wall with some delta barrier. I mean, we're gonna get B delta of x for x smaller than L, and infinite for x absolute value larger than L. It can be drawn. This is x. This is Vx. It can be drawn like this. So here we can have this is minus L, this is plus L. We can be over here, and here we have a delta function. Right. The Schrödinger equation reads minus h bar squared over 2m d squared dx squared psi of x equals e psi of x. And now you say, oh my, you forgot the delta potential. No, I haven't forgotten. Because this is true for everywhere except a specific point. And the only way we're going to see it is when we are doing the boundary condition on x equals naught. Meaning, we do say that psi of x is equal to a cosine kx plus b sine of kx for x between 0 and L, and minus L, and c cosine kx plus d sine kx for x between L and 0, and 0 otherwise. We do claim that we have different solutions, however, we have the same wavelength or the same quantum wave number k, and the potential, the delta potential, is going to matter only when we try to stitch or sew or connect those two solutions. Okay. The most important note regarding this kind of potential is this potential is symmetric. So when a potential is symmetric, you learned in the lecture that we must have either odd solutions for the wave function or even solutions. You can't have something which is not strictly odd or even. Because we can't have something which is strictly odd or even. For example, something which is not odd and not even is something which goes like this. It's not odd and it's not even. Cosine is even, zugi. Sine is odd, izugi. So because we can't have, what we can do is we can separate this solution and solve first for the even case and second for the odd case. Why does it help us? It helps us because it gives us some restriction over the system and it makes the solution easier. Solving for the even case basically meaning psi of x equals to minus psi of x, we get that c cosine kx, and just putting the something, I choose some x from here, and here the minus x, because my minus x, and I just apply it like this. So this is psi of x equals to psi of minus x. So c cosine of kx minus d sine of kx equals to a cosine of kx plus b sine of kx, which implies that a is equal to c and b is equal to minus d. You're free. So, just using the fact that psi is even, we found already two conditions. Questions? Okay. So let's write here on the right, psi even of x is equal to a cosine kx plus b sine kx. Here we're gonna have a cosine kx minus b sine of kx. This is for left, this is for right. Okay? Perfect. This is just putting here the constants. Boundary conditions are psi of minus L minus equals to psi of minus L plus, psi of L minus equals to psi of L plus, basically here and here, psi of F0 minus equals to psi of 0 plus, so it's basically just a continuity condition. And we can also talk about the boundary, about the delta function, because we can also say that h bar squared over 2m psi tag of 0 minus psi derivative of 0 plus is equal to beta psi 0. Okay. Basically, all those we know how to do it. We got it familiar, and here we got the delta. However, what's interesting, and what we are soon gonna see or not, because we don't have a lot of time, is that for the odd case, we are not going to have this delta function. Why? For the even case, we get this condition of this delta function, but for the odd solutions, we are not going to have the delta function, because the delta function is even, is an even function. In Hebrew you want? No? Okay. I'm gonna skip a few steps because you're gonna do it in your homework. Very good. Basically, when we impose those conditions, similar to what we had in the first part of this lesson, we get an transcendental equation. Great. We basically get that an equation which reads, and I'm gonna write it over here. It's gonna be nice. Tangents of KL is equal to minus h bar squared over ml beta KL. So this is very interesting because if we try to go back two lectures ago, we solved the infinite well question, the infinite well example. For this case, we didn't have some transcendental equation. So the only way we get such solution is going to be due to this delta barrier in the middle. This delta function, which is like an obstacle in the middle, this gives some condition for the quantization of the problem. If we didn't have a delta barrier, which is going to be what we can see when we solve for not the even case, for the odd case, what we're going to get is the simple known solutions for the infinite well. Okay. So I said everything which is highly important, in my opinion. What I want to do is I want to solve this equation, because this is something we should know. You should know how to do good, because it's hard. So we start by doing the axis. Let's say this is an axis for KL. Let's be more rigorous. I'm gonna erase everything over here. Now all we're gonna do is try to focus on this single equation and solve it. So we can define theta to be KL, and we can define let's call it let's call it eta is going to be equal to h bar squared over ml beta. So what we have tangents of theta is equal to minus eta theta. I always prefer to do it in this way, to define all the positive constants, because everything here is like minus some positive number. This must be a positive number. So I always have to define it in such a way which is very easy for me to understand. Okay, so let's draw it. Yeah. We can have here. So how does tangents looks like? So we're gonna try to be a little bit more precise than previous time. We're gonna write here pi over 2. Let's write it from the formula. Pi over 2 pi 3 pi over 2 pi. Perfect. So this is the tangents of TL. Now it's very easy to just write for the different values of eta this relation. We can use this kind of eta, maybe this kind, maybe this kind. So when the eta is, let's ponder for a few seconds. So what does it mean when eta goes to 0 to infinity? Okay, so now we know that we have here the solutions. Maybe here we have another solution, and so on. So we have all those solutions, which are the bound states of this problem, determined by this delta barrier. So what we want to ask is, okay, let's look when beta, the delta barrier, goes to 0. This, if beta goes to 0, eta goes to infinity. Then talk about it, if beta goes to infinity, eta goes to 0. So when let's make sure. So when beta goes to 0, we basically don't have a barrier. It's very thin, it goes to 0. So the wave function of the particle doesn't see it at all. And what we get if we use some, and I just don't know how to do it because we don't have a lot of time. So what we can do, we can look at the algebra more carefully and find that we get the regular potential well solution also for the even case, because if beta goes to 0, we basically don't have any barrier in the middle when you have the potential well. When beta goes to infinity, n goes to 0, and we get an infinite number of solutions, basically. That's a bit it's a bit more delicate, maybe, those limits. This limit is a bit more delicate, so I'm just gonna notice it. Okay, any question regarding this idea over here? Yes.
It means that there's infinite possible energies because there's.
Yes, there always are in those kinds. Like you see here, if I draw this line to each of those lines intersect tangents KL infinite amount of times, because even if the slope is very small but not 0, when you go to infinite, a state can go to anywhere, to any theta. You will meet.
And it seems for the other question, yeah, the other example.
For the first example, you didn't have infinite amount of energy levels. You had finite amount of energy levels or finite amount of bound energy levels. Because you mean the previous example we did today?
Yeah.
Yeah, that's it.
Okay.
Okay. So for the previous example, we had something which looked more like, what was it? Cotangents?
It was cotangents and the square root of
So it looked more like this was the cotangents, and the square root of something looked like this. Or this, for example, and stopped here, always. So for the right black line, we have two possible solutions. For the left black line, we have 0 possible solutions. Here, we always have an infinite amount of solutions. It's because we had different cases for different potentials. Here, we always are still in some infinite world potential, and the delta function, it changes the quantization of energy levels. It changes, it interacts, it makes it a little bit different in some manners, and you can see it here.
Yeah.
But if we consider the case where the potential barrier goes to 0, we still get infinite potential well, and still we have infinite amount of energy levels as we accept it to have. Okay, bye.
תודה רבה.
Okay.
אפשר שאלות בלי קשר?
לא.
אוקיי, טוב, ינסו.
מה?
ככה, בחלק הראשון, בדוגמה הראשונה, אז כאילו הנחנו שלא יכול להיות גל שחוזר כדי שיהיה לנו דעיכה בתוך הבור.
זה לא הסיבה.
זה לא
אני
הסיבה.
גם יכול להניח את זה, אבל זה לא הסיבה כי לא הלכנו תנאי התחלה.
זהו, זה...
מה שאנחנו אמרנו כזה דבר. בדוגמה הראשונה, אמרנו אוקיי, נניח שיש לנו איזשהו גל שחי פה, אז יש לנו A, E ב-I, K, X ימינה, B, E ב-I, K, X שמאלה, ואני יכול לכתוב פה C, E ב-I, K, X ימינה, ו-D, E במינוס I במינוס.
זה לא היה אפילו להתבדר או משהו?
נכון.
זהו, אז אני שואל אם זה לא כמו תנאי שפה מסוים, או תנאי התחלה מסוים.
לאט לאט. אז זה באופן כללי. אנחנו בדיוק מסיימים, עוד 5 דקות מסיימים.
כן.
אז זה באופן כללי. אחרי כי יכול להתחיל פה, יכול להתחיל באמצעות, זה לא משנה. אז עשיתי הגבלה כזאת. אני אמרתי ש-E קטן מ-V0, הנחתי את זה. הסתכלתי במקרה הזה, ספציפית.
אוקיי.
אם E גדול מ-V0 אנחנו מקבלים מה שלנו תרגול שעבר, וזה לא כזה מעניין, כי כבר עשינו את זה. עבור E קטן מ-V0, אנחנו מקבלים, סליחה, פה כתבתי כי התכוונתי לכתוב Q.
כן.
אנחנו מקבלים ש-Q מורכב, Q קומפלקס, כך שאני יכול להגיד שהריל של Q שווה ל-0. כלומר אני יכול להגדיל Q טילדה שווה ל-IQ, ואז יש לנו פה CE ב-Q טילדה X מינוס Q טילדה X, כך ש-Q ממשי, Q חייב להיות ממשי, נכון?
שמת שם Q טילדה והוא מרוכב,
Q טילדה זה על Q,
ריל של Q טילדה
שווה ל-0, זאת אומרת, זה אומר
כן.
ש-Q שווה ל-A ועוד BI, אז A מת, כי הריל שלו הוא 0.
נכון.
אז אם אני מכפיל את זה ב-I, אני מקבל משהו ממשי.
כן.
תודה רבה, חולה עליך, ביי.
בכיף.
וזה נובע הכל מההנחה של
ש-E קטן מ-V0. שזה גם הגיוני, כי אתה אומר, אין לי מספיק אנרגיה כדי לחיות בצד הזה.
בצד הזה, סבבה.
אז מה שאני מקבל, אז פה איפה שיש לי מספיק אנרגיה אני מקבל אוסילציות.
אז זה כן תנאי התחלה.
זה לא תנאי התחלה.
אני מתחיל מאנרגיה נמוכה.
וזה לא תנאי התחלה, זה לא באיזה אנרגיה ספציפית. אני מתחיל איפשהו באנרגיה שהיא פה, אני לא יודע איפה. אני יכול להיות 20% סיכוי שלי באנרגיה הזאתי, 20% באנרגיה הזאתי ו-60% באנרגיה הזאתי.
הבנתי.
מההתחלה זה מה הדיסטריביוציה של האנרגיות האפשריות, מה הסיכוי לכל אנרגיה
בזמן מסוים.
בזמן t שווה 0. זה מההתחלה.
הבנתי.
אם יש רק אנרגי בנד אחד, רק רצועת אנרגיה אחת, אז מן הסתם שאנחנו יודעים מה הם תנאי התחלה, כי אין לנו...
אז הכל יצאת מנקודת הנחה שאי אפשר לעבור את המחסום אנרגיה הזה, ושאם אני לא יכול לחיות בצד השני, ובגלל זה כתבת את זה.
זה גם נובע ישירות מהמתמטיקה, זה שיפה.
כן.
אם אני מלכי קטן מביא 0, אנחנו מקבלים שהקיוטילדה הזה הוא משהו ממשי,
נכון.
טהור, הוא לא מורכב בכלל.
נכון.
אז עכשיו אני מקבל פה שתי תוצאות. אוקיי, עם התוצאה השנייה של המינוס QX, איך זה נראה? זה נראה כמו אקספוננט דועך, נכון? זה המינוס.
זה סבבה, והשני מתבדר.
משהו מתבדר. ואני לא חושב שלי משהו מתבדר. למה? אתה מסתכל
זה
פה
לא
על PDF.
פיזיקלי, אמרנו שזה... זה לא יצא לי גם אחד, וזה גם...
זה בחיים לא יצא לך... אתה לא צריך לנרמל את זה בחיים. אם יש לך משהו שהסיכוי למצוא אותו גדל עם X, אז הסיכוי שלו, אתה לא יכול לנרמל את זה.
נכון. אוקיי. ושאלה שנייה, אני לא יודע אם זה... כמה זה קשור, אבל... אני מחפש את זה